If you were to write out a particular pattern of bits, I don't know, I'm writing some values here. Okay, so this particular, let's do another one here, we'll have that as high, high, high. So at a particular point in time, this is high, this is high, this is high, low, low, high, low, high, low, low, high, high. And this is high, low, low, high, low, high, for example. So you've sent them out on these parallel wires and they're changing at the same time. When they arrive at this point, we need to read in the values. We have to sample the data. Okay? So using either a clock signal or something, we look at a particular instant in time, what value do I see here? Now, obviously there's going to be some kind of propagation delay and these things are going to appear here. And we're going to sample it at different times to read in these values. Okay? The problem is the time it takes for the signals to go on these wires from here to here will be different from one wire to the next. Might not be that different, but it will be enough so that if you try and do this at high speed, if you, for example, if you think of a transition here, let's just simply do a low to high transition. If you had sent at exactly the same time a low to high transition at this point here, and you looked at what happened over here, you might find, if this is a sort of timing diagram, that this one goes low to high here, this one goes low to high here, this one goes low to high here, low to high here. They may not all transition at exactly the same time. Effectively, this is a kind of, this is known as skew. Okay? Generally speaking, from the days of you, I don't know if any of you ever bothered building desktop computers and things like that, we used to have parallel wires that connected the hard disks to the motherboard. And as a typical rule of thumb, you might have a hard disk connected to the motherboard over here, and this would be a parallel set of conductors, and this would be known as your IDE cable. And you would typically be allowed to make this centimeters long, 60 centimeters long. And I think the fastest speed you could get it to go was about 133 megabits per second. Something like that. If you tried sending data faster than that, the problem is that things which were aligned at one end of it would be sufficiently skewed with relation to each other at the other end. If you were to sample it, in some cases you're sampling the new pulse that's just arrived, and in some cases you're still sampling the old pulse that hasn't been updated. So with parallel conductors, if you're doing things at low speed, it's not a problem. If you start to try and transfer large amounts of data in parallel at high speed, skew becomes a real issue. The solution to doing that is to basically say, well, let's not try and send lots of signals in parallel, let's just send one signal at a time. So if I've got to send binary the value, I don't know, let's just have a nibble. So I could send on 4 separate conductors this value, 1, 0, 1, 1. Alternatively, I can just have one conductor and I send 1 followed by a 0, followed by a 1, followed by a 1. Now, okay, it's got to be sampled at the right time, but there is no skew that's going to arise in this case because there's only one line to sample. Whereas in the case of the parallel conductors, even though you send them out at the same time, the signals might arrive slightly differently, some slightly later, some slightly earlier in relation to each other. And it's hard to predict because it might be down to the manufacturing properties of the cable that you happen to be using. So as a rule of thumb, when we go for very high-speed communication, we don't use parallel cables because of this problem of skew. What we tend to do is we move to serial communication, where we only transmit individual bits at a time. And in fact, in the case of hard disks, I suppose those of you these days, in the old days it was called, you might come across this term, parallel ATA. I forgot what the ATA stands for. We don't have that anymore, it's serial ATA. So in fact, to access information on hard disks now, we don't use parallel cables anymore, we use a single serial cable. Because the transfer rates from the hard disk to the motherboard are much, much faster, and you couldn't do it reliably with a ribbon cable. Okay, so in terms of getting systems to talk to each other, if they're talking to each other at relatively low speeds, there's nothing wrong with using parallel conductors. If you're trying to transfer information between entities at high speed, sooner or later we end up switching across to serial communication. Certainly most microcontrollers that I know of provide, because serial communication is such a common thing, they often provide hardware support built into the microcontroller for serial communication to make it a bit easy for you, or easier. So, this is just very general terminology associated with serial interfaces, in fact with any kind of communication system. In a communication system where there's only ever one thing transmitting, another thing listening, and nothing needs to come back in the opposite direction, we talk about that as being simplex communication. I think you've done all this before anyway. If you basically have some kind of communication system where actually the communication is bidirectional, but only one direction at a time, we talk about that as being half duplex. If you had a single bidirectional bus that's shared between devices, that would be an example of a half duplex communication system. However, you can have systems where you can transmit and receive at the same time. Under those systems are known as full duplex. And the 8051 is capable of full duplex serial communication. Right. Let's talk about synchronous and asynchronous serial communication now. Fundamentally, let's just blank this a minute. In serial communication, I've got an entity A wanting to talk to an entity B. And the entity A is going to send out bits of information. So let's say it's going to send out the pattern 1101. Okay, or if you want to see that going in this direction, time, it would go high for a bit, high for another bit, then low, and then high again, and then we don't know what happens out over here. Okay. There's a couple of things associated with this that we need to be aware of if entities are talking serially. One is we have to agree, if we wanted to send out, now this could be the value, what is that in binary? Not in binary, in hex. That's, is that D? Yep. That's the letter D. It's D if we assume that this is the most significant bit and this is the least significant bit. If we read it this way round, then we'd end up with this value, which is, what's that, 1, 2, 4, 8, 10, 11, which is a B, isn't it? Yeah, a B. So, one thing we have to be careful of in a kind of serial communication system is both entities have to agree, is it the most significant bit that's getting sent first, or is it the least significant bit that's getting sent first? And don't believe that all systems always agree the same way of doing it, because they don't. But in terms of the 8051, I think it's the most significant bit first. Okay? So that's one thing. So there has to be some kind of agreement between the entities about which bit's the most important, if you like, the most significant. Is it the first bit that I get and the least significant bit is the last, or vice versa? Second thing, and this is what brings me on to synchronous and asynchronous. You're going to have these pulses arriving at B. How are you going to know, what the values are? here's the pulses coming in. Zoomed in a little bit. You have to be able to, what we call, sample those pulses at the right time instance. Basically, you keep looking at that pin. Here's that wire coming in. You have to look at it and say, okay, is it high or low? So you look at it here, you say, is it high or low? Oh, it's high. Is it high or low? Oh, it's high. Is it high or low? It's low. Is it high or low? It's high. What matters is the timing of when we sample it has to correspond to the bit rate that we're transmitting at. Furthermore, the first sample really needs to be halfway through when we're transmitting the first bit. There's a kind of a half period where we want to wait. We don't want to sample it at the edge. Because if you were to sample at the edge, if you sample at this point, well, it's touch or go whether you're going to sample it as a 1 or a 0. To get reliable communication, you need to transmit at a certain rate, and you need to sample at the same rate, but the sampling is slightly offset with when the bits arrive. You want the first sampling instant to be half a period later than when the first bit has arrived. And then you hope to sample it effectively in the middle of those subsequent pulses. So far, so good? How do we know when to sample it? There are two main ways of achieving this, known as synchronous serial communication and asynchronous serial communication. In synchronous serial communication, the clock that controls when to sample the pulses is given to the receiver from the transmitter. Now, that could be in one of two ways. One way is, here's the data, and separately I have another line that goes in which contains the clock. And I've got a ground plane, I've got some kind of ground signal if you want. So there's the ground. So that's the first way of doing it, is effectively the transmitter that sends the data also sends the clock that controls when to sample. That's an example of synchronous serial communication. The problem with this system is, in addition to the ground signal, I've got my data wire and I've got a clock wire. I need 3 wires to build my communication system. There is another way of achieving this synchronously. Where effectively I might send, and let's do an example. What we've got here is, for a little while, the transmitter sends just 1 0 1 0 1 0 lots of times. And after an agreed number of 1s and 0s, it then sends the data. In this case, 1 1 0 1. You can have inside your receiver a special circuit known as a phased lock loop. You don't need to worry anything about the details of this, but basically you can feed this information, so your data is kind of coming in, but it's also feeding into this, which also, and that then controls when to sample the data. So what happens when the data starts to come in, the 1s and 0s cause this phase lock loop to start oscillating at a certain frequency. And once it's oscillating at that frequency, it kind of is able to do that pretty reliably for quite a long time. So you basically send something to excite the phase lock loop, get it oscillating, and then you tag on the data at the end of it. So the local oscillator at the receiver is oscillating a frequency that's determined by the transmitter, because it's the transmitter that sent out the 1s and 0s. So in this particular system, the speed or the frequency of the phase lock loop is almost, it's identical to, if you like, the speed at which the 1s and 0s went out of the transmitter. And for a while, after you've stopped sending ones and zeros, while the data's going across, you'll be sampling it at the right instance. In this particular case, the clock that's used to sample the data effectively has been derived from what the transmitter sent you. So this is another example of a synchronous serial communication system. And this is the way that Ethernet works. Okay? And you all know about Ethernet, that old-fashioned wired thing. Okay? It's a serial communication system where the synchronization, you don't have a 3-wire Ethernet, it's actually a 2-wire system where the clock is recovered from the signal that comes in. The 8051 can't do that. Okay? The 8051 is simple and cheap. Ethernet controllers are complex. Phase-lock loops are expensive. At least they used to be. So there is a different type of communication system, serial communication system, which is used by things like the 8051. And in the case of the 8051, let's say the transmitter is transmitting at a bit rate of, say, 9,600 bits per second. The receiver, we configure it to read at 9,600 bits per second, but the problem here is it's going to use its own clock source as a reference for that speed. And the transmitter is using its own clock source, so they're not actually sharing the same source of the clock signal. What we've done is this has got its crystal, so this might have a 12 megahertz crystal that's being used to generate pulses at this rate. And this has got its own 12 megahertz crystal, for example, or it could be a different speed, but effectively is being used to derive something that should be at the same rate. But it's not guaranteed to be exact. Okay? And if you're only sending short amounts of information, you can get away with this. So what we basically do is, in this case, we say that, okay, let's say the receiver wasn't exactly 9,600 bits per second, but the transmitter was. So here's the data arriving. Provided we can work out where the pulses are starting, we might sample here for the first one, the next one might be here, the next one might be here, the next one might be here. You can see the alignment isn't quite perfect. But if you look at the interval between these, it isn't quite the same as the interval between those. But if it's close enough, you can still sample the data appropriately, provided you're not trying to sample too much data. This error is kind of accumulative, and if you carry it on for longer and longer, eventually you'll start sampling the wrong pulse, or you'll miss a pulse. Okay? You can draw this yourself if you want. If you might say, well, here's some data, and what's the difference in here in terms of time? We might say, well, that's going to be 1 millisecond, 1 millisecond, 1 millisecond, and so on. You might say, okay, let's start sampling this half a millisecond into that, but actually the interval at which we sample isn't 1 millisecond, it's 1.1 milliseconds. You could work out what the interval would be here, and you'd see that these would start to be further apart, and eventually you'll miss a pulse. Okay? But provided we only send very short amount of, is that right? We send little bits of information. And then at the end of that, we send another little bit of information, and the clock starts again from that point. Provided we start more or less in the middle on the first pulse, even though the timing isn't identical, we can get away with sending at least a few bits of information and sampling it at more or less the right rate that will actually be able to read it correctly. That technique, where the sender clock that's used to transmit the data and the receiver clock, which is used to sample the data, are not derived from the same source, is known as asynchronous communication. And that's what the 8051 uses. It uses an asynchronous serial communication system. And at most of the kind of speeds that we're talking about, a percentage error of a few percent is okay. And we only send 8 or 9 bits of information at a time. And a few % error with 8 or 9 bits at a time, you can get to work reliably. So, so in order to accurately read the data, you have to sample it at the right instance. How do you know how to sample at the right instance? You've got 2 choices. Either the sampling clock is derived directly from the transmit information, either as a dedicated clock line, or you recover the clock from the data using something like a phase-lock loop. Alternatively, you have an asynchronous communication system where the sampling clock isn't derived from the transmitter, but it tries to be almost the same speed. And even though there might be an error, provided the error is small, we can get away with it. Okay, so that's just saying the same kind of thing. When do things start, and when do you need to know when to start sampling? That's what this slide is about. Traditionally, you don't have to do this, but normally in an asynchronous communication system, or most serial communication systems, when we're not transmitting data, we often leave the serial channel in a high state, for example. So it's at logic 1, high. So when nothing's going on, it's high. Then when we want to start transmitting the data, the first thing we do is to make it go low for a certain period of time. And all communication starts with this high to low transition. This transition has got nothing to do with the data that you're sending. So if you're going to send 1101, this precedes the data that you're transferring. This is known as the start bit. Now, usually it's just 1 bit, but it could be 2 bits. You can have systems where it's 2 periods of it being low. Or it might be low followed by a high always. But in our case, we'll say there's going to be 1 start bit, then your data. So there'll be 4 pulses of data. These should all be the same width, by the way. My drawing's not very good. And then at the end of it, you'd have a stop bit, which, for example, is always high. So start bit, always low. Stop bit, which is always high. And then this is idle. And this is idle. Oops, can't spell. So this, in this R case here, this would be the 1, 1, 0, 1 here. This would always be high, and this would always be low. Now, why am I doing that? Because when I'm sampling this, I know this transition will wake up the receiver and get it to start sampling. The very first thing it should sample must be a 0. If it's not a 0, it knows something's gone horribly wrong. The next thing it will assume is data, 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 data. The last thing it's going to sample, it knows it should be a 1. If it's anything other than 1, it knows it's gone horribly wrong. So the start and stop bit, the start bit wakes things up. The stop bit gives us some kind of reassurance that things are working okay, because the very last bit we sample should always be a 1 in this system. So this is the data. So basically, yeah.
If it can understand the start bit and the stop bit, fine, it wakes up and stuff, and it knows it's 8 bits, why would you even need to start and stop bit? Why can't you just know?
The problem is, let's say it's idle high and you're transmitting 1, 1, 1, 1, 1, 1, 1. It's just going to be high. There's no transitions at all for a start. So the start bit is there to force a transition on this wire. When we're saying the idle state is, for example, high, the start bit is always low. So when a communication starts, we force a transition.
So is the clock decided from the length of that start bit then?
In this particular case, no, it isn't. It's designed from, the transmitter and receiver are kind of, by some magic beyond our communication system, they've been programmed to be more or less the same value. But what the start bit will do is, given that it's sampling, if you like, the rate of receive, it will basically, when this transition happens, it will count, depending on what you've configured the receiver clock to be, effectively a certain point from that transition for the first sample. But the time from when that transition takes place to where you do the first sample is based on what you configure the receive clock to be.
If they're both locked together, why would it matter if it's all ones forever? Because it's still something that appears to see.
What's locked together? The transmitter and receiver in an asynchronous system are not locked together.
Well, not locked together, but they're set at the same.
That's not perfect. Just because you think they're both at 9,600, they won't be. One might be 9,607, the other one might be 899 or something.
No, definitely, because it's not sampling all the time. It only samples when it goes.
There's quite a reasonable amount of variation. If you had perfect synchronization, then all you need is something to wake it up and say, now's the time to start sampling, and then everything else will be fine. Yes, absolutely. And that's effectively what we're doing more or less with a synchronous system. But in an asynchronous system, those clocks are only approximately the same thing.
So it's more like to, yeah.
It's fine if you're only sending a few bits.
Yeah, no, okay.
But if you let it go on for too long, you'll start to misread information because you'll be sampling, you might miss a pulse, or you might sample the same pulse twice, whatever. So in an ordinary asynchronous communication system, we normally have the wire set in an idle state, which is usually high. The nice thing about that is if it breaks, you can sense that. So we're normally at a certain logic 1. And then a 1 to low transition wakes up the receiver sampling circuitry, and based on its own local clock, from the point of that transition, it will say, well, if I'm sampling at 9,600 bits per second, I know approximately how long to wait from that transition to do my first sample, which will be half a period. And then thereafter, it will be one period apart, it will do its sampling. But that one period apart is derived from its own local clock, not of the transmitter clock. And it knows that the very first sample it does should be a 0. If it's not a 0, it's wrong. It's then going to read a certain number of data bits, and it knows that the last sample it should do will always be a certain value, in this case, logic 1. After that, it goes to sleep again. So provided the first bit it sampled was a 0, the last bit it sampled was a 1, it will treat the samples it took in between those as being valid. So. I think I've got a little kind of illustration. So here's a typical system. This is actually not quite true here. There should be a little green arrow here because you would actually check the start bit as well. So there'd be a little thing here, and then this is the data, there's the stop bit, and then it going idle again, waking up again here, and then the next piece of information. Okay. So in asynchronous communication, you can, sandwich between your start and stop bit, you can typically send about 8 data bits, and you can have a few % error between the transmit clock and the receive clock. But if you work that out, that effectively means that about 20% of the time on the channel, we're not actually sending useful data, we're sending either start bits or stop bits, or it's idle. So it's not the most efficient of communication systems. Whereas with synchronous communication, okay, you need to send that, for example, in the case of Ethernet, you need to send for a short bit of time a number of 1s and 0s to get the phase lock loop to do its thing. But phase lock loops, once they're kind of oscillating at a certain frequency, they will oscillate at pretty much that frequency for a pretty long time. So in the case of something like Ethernet, one frame of information could be where you can see thousands of bytes long. Now, preceding that thousands of bytes, there'll be a couple of bytes where it goes 10, 10, 10, 10, which is known as the preamble. And during that preamble, we're basically getting the phase lock loop to do its thing. But once it starts oscillating at the appropriate frequency, we can actually have